Dear students, in the last class, you have studied about the solids. In the solids, we have studied about the elementary ideas of the structure of the solids. Today, we take about the symmetry in crystalline solids. So, symmetry is nothing but the perfectness. As you know, the crystalline solids, the atoms are arranged perfectly in a definite manner. So this symmetry leads to the stability. The constituents of a crystalline solid are arranged in an ordered, repetitive fashion in 3 dimensions. The array is called the space lattice. A peculiar regularity is observed in the arrangement of these constituent units in a crystal. Crystals can be classified according to this regularity in arrangement of atoms, ions, or molecules, or in other words, their symmetry. The study of symmetry of a molecule is often useful in making its theoretical and experimental treatment simpler. For this purpose, a point is marked in the molecule and symmetry with this respect to lines and planes passing through this point is considered. Thus, when a symmetry operation is performed, at least one point does not move from its position. The geometrical entity such as a plane or line with respect to which a symmetrical operation is carried out is called symmetry element. Several types of symmetry elements are used to describe the symmetry present in molecules and crystals. These include identity element, axis of proper rotation, a center of inversion, mirror planes, and axis of improper rotation. It may, however, be noted that all these elements may or may not be present in a given case. So, as the brief what I have said about the crystal symmetry is the crystals have an inherent symmetry. Because of that symmetry, the crystals are highly stable. The definite ordered arrangement of the faces and edges of a crystal is known as crystal symmetry. It is a powerful tool for the study of the internal structure of crystals. Crystals possesses different symmetries or symmetry elements. Now the same thing as I have said in my earlier, symmetry is the important property of a crystal. The geometrical entity such as a plane or line with respect to which a symmetrical operation is carried out is called the symmetry element. Of course, the several types of symmetry elements are used to describe the symmetry present in molecule and crystals. Out of these, let us study only the elements of symmetry. There are 3 types of elements of symmetry are there. Number 1, plane of symmetry. Number 2, axis of symmetry. Number 3, center of symmetry. Now, let us restrict our study to this symmetry operations for a cubic system. So, imagine a cube. So imagine a cube. So when I take this cube contains the 6 faces. Here I have shown the opposite faces. One face, second face. These are the 2 opposite faces, and this is the third opposite faces. So a cube has 6 faces. Now the same cube also has 8 corners. These are the 4 corners at the top, and these are the 4 corners at the bottom. So it contains 8 corners, and then this cube has the 12 edges. These are known as edges of a cube. The 4 edges are there at the top, and remaining 4 edges are there at the bottom, and these 4 things are linked like this. So therefore the cube contains, this is a very important, it contains 6 faces, 8 corners, and then 12 edges. Keeping this point in mind, now coming to the plane of symmetry. It is an imaginary plane passing through the center of a crystal, by which the crystal is divided into 2 halves, such that one is the mirror image of the other. I repeat, imagine a cube. You divide the cube into 2 halves. That means you cut the cube by putting a plane touching the 2 faces. Then the cube divides into the 2. One is the mirror image of the other. This is called plane of symmetry. In cubic crystal, there are 2 types of planes of symmetry. One is rectangular plane of symmetry, and another one is diagonal plane of symmetry. Rectangular plane of symmetry are the planes situated midway and parallel to the opposite faces. As I have said, how many faces are there in a cube? There are 6 faces are there. So when there are 6 faces, or it is also called 3 pairs of opposite faces in a cubic crystal, therefore it contains 3 rectangular planes of symmetry are possible. 6 faces, up half of that, it is 3 planes of rectangular planes of symmetry are there in a cubic system. Coming to the second one, the diagonal planes of symmetry. These are the planes touching the opposite edges. There being how many edges? The 12 edges, or 6 pairs of opposite edges in a cubic crystal. Therefore, we have 6 diagonal planes of symmetry are possible. In this diagram, as I have said, so rectangular planes of symmetry. So this is a rectangular planes of symmetry here. So in this rectangular planes of symmetry, so you have 6 faces are there. Now if I take these 6 faces, and if I, what you can say, the touch, if you cut them, so how many planes of symmetry you get? You get 6 planes, 3 planes of symmetry we get. These are called 3 rectangular planes of symmetry. Now in case of diagonal planes, how many edges are there? There are 12 edges. So therefore you have the 6 diagonal planes of symmetry are possible. In total, we have 9 planes of symmetry. That's what it is said. There being 6 faces or 3 pairs of opposite faces in a cubic crystal, so we have totally the 9 planes of symmetry. Coming to the axis of symmetry. It is an imaginary line passing through the center of a crystal about which the crystal may be rotated such that it presents the same appearance more than once during the complete rotation. Try to understand the statement. It is an imaginary line passing through the center of a crystal. Imagine a cube about which the crystal may be rotated such that it presents the same appearance more than once during the complete rotation. In a cubic crystal, there are 3 types of axis of symmetry. Number 1, axis of 4-fold symmetry. Number 2, axis of 3-fold symmetry. And number 3, axis of 2-fold symmetry. Coming to the axis of 4-fold symmetry. It is an imaginary line passing through the center of 2 opposite faces of a cube. On rotating the cube about this line as axis, it will be found that the cube presents exactly the same appearance 4 times in one complete rotation. What's the meaning of this? So that we will take it here. How many faces are there? There are 6 faces. It means 3 pairs of opposite faces. You pass a line in this. And when we pass a line, so we get the 3 4-fold axes of symmetry are possible. These are at right angles to each other. So this I wanted to explain. 6 faces are there. So half of that is 3. So we have 3 4-fold axis of symmetry. Coming to the axis of 3-fold symmetry. It is an imaginary line passing through the opposite corners of a cube along the body diagonal. On rotating the cube about this line as axis, it will be found that the cube presents the same appearance 3 times in one complete rotation. Now in this 3-fold axis, which are the things? The corners of a cube are considered. Opposite corners, a line is passed. So how many corners are there? There are 8 corners. Then how many axes of symmetry you get? Fold. We have 4 3-fold axes of symmetry are possible. This is what it is written. Coming to the axis of 2-fold symmetry. It is an imaginary line passing through the center of 2 diagonally opposite edges of a cube. On rotating the cube about this line as axis, it will be found that the cube presents the same appearance 2 times in one complete rotation. Now, here, this is what I wanted to say. The 4-fold axis of symmetry, you take a cube. In this cube, the line axis is passing through the faces. When it is passing through the faces, what is the revolution degree, 360 degree. It's a fourfold. So each fold will become 90 degree. That's why we say 360 divided by 90 gives fourfold. It means for every rotation of 90 degree, the cube appearance will be the same. Every rotation of 90 degree, the cube appearance will be the same. Hence it is called fourfold axis of symmetry. Now since there are 6 faces, you have 3 fourfold axis of symmetry are possible. Coming to the threefold axis, it is 360 degree divided by 120 gives threefold. And in the threefold axis, the corners, opposite corners, you are placing a axis. Now every rotation of 120 degree, the crystal appears to be the same. So since how many corners are there? 8 corners are there. We have 4 threefold axis of symmetry. Coming to the third one, the twofold axis of symmetry, the total angle is 360 degree divided by 180 degree gives twofold axis. And the twofold axis of symmetry, here the edges, the line is passing through the edges. How many edges are there? Totally there are 12 edges. Therefore, you have 6 twofold axis of symmetry. It means by rotating the crystal about 180 degree, the crystal appearance along the edges, the crystal appearance will be the same. In total, how many axes of symmetry? 3 plus 4 plus 6 gives 13 axes of symmetry. This is what I have written here. There are 12 edges or 6 diagonal opposite pairs of edges. So 6 twofold axes of symmetry are possible. In total, there are 13 axes of symmetry in a cubic system. Lastly, coming to the center of symmetry. You take a cube. In the cube, you have only one center. If you take a circle, you have only one center. You don't have multiple centers. So that's what it says. It is such an imaginary point within the crystal that any straight line drawing through it will intersect the faces, edges or solid angles of the crystal at equal distances on opposite sides. It's a very important statement. A crystal may have either one or no center of symmetry. Of course, in cubic system, a cube has one center of symmetry. It can never have, generally a crystal never have more than one center of symmetry. The number of elements of symmetry in a cubic crystal is 9 plane of symmetry, 13 axes of symmetry and 1 center of symmetry. Overall 23 symmetry elements. Here this is a diagram showing the plane of symmetry. As I have said, how many planes of symmetry are there? You have 3 rectangular planes of symmetry and then you have 6 diagonal planes of symmetry. Overall 9 plane of symmetry. Here this is what I have shown, the diagram, the 3 rectangular planes of symmetry and the 6 diagonal planes of symmetry. Now coming to the axis of symmetry. This is a diagram. It shows we have three four-fold axis of symmetry. We have four three-fold axis of symmetry, and then we have six two-fold axis of symmetry. Overall, 13 axis of symmetry. And then, as I have said, in a cube, you have only one center of symmetry. Overall, elements of symmetry in a cubic crystal is 23. So, the students, you must know how many rectangular, how many diagonal, how many axis of four-fold, three-fold, center. These numbers you have to remember. Coming to the another point known as laws of crystallography. Crystallography is the branch of science which deals with the study of geometry, properties, and structure of crystals and crystalline substances. In this crystallography, we use the following terms very oftenly. That is, the phase, edge, interfacial angle is also done by the corners, and then the zone and the crystal habit. Phase is the plane surface of a crystal, which are called the faces of the crystal. The edge, it is a line along which the two adjacent faces of a crystal intersect. Interfacial angle is the angle between the adjacent faces of a crystal. A set of faces which meet in parallel edges is known as a zone. The external shape of the crystal is called crystal habit. The relationship between the phase, edge, and interfacial angle. Interfacial angle is also nothing but it is the corner. So the relation is given as phase plus interfacial angle, that is F plus C is equal to edge plus 2, E plus 2. Coming to the cubic system. You know, in the cubic system, you have 6 faces, then 8 corners, and then the 12 edges. So, the F is 6, C is 8. 8 plus 6 is 14. You have 12 edges. 12 plus 2 is also 14. Take another example as hexagonal system. In hexagonal system, so we have the 6 angles at the top and 6 angles. Totally we have how many faces are there? The 6 faces, and top and bottom you have 8 faces are there in hexagonal system. You have 6 top and 6 bottom, 12 corners are there, and then the 6, how many edges? The 6 edges at the top, 6 edges at the bottom. These two are connected by the 6. So totally we have 18 edges. Therefore, so it will be 8 plus 12 is equal to 18 plus 2. This is how the relation holds good. Coming to the laws of crystallography. So crystallography is based on 3 fundamental laws. First one, law of constancy of interfacial angles. Number 2, the law of rational indices. And number 3, law of constancy of symmetry. Coming to the first one, the law of constancy of interfacial angles. The crystals of a substance are obtained by cooling the liquid or solution of that substance. We know when the liquids are cooled, we get the solids, the crystalline solids. Similarly, when the solutions, the crystalline solutions are cold, we get the solid crystals. The size of the crystal depends on the rate of cooling and pressure of any other presence of any other substances. We know the slow cooling results large size of the crystal, and fast cooling results the small size of the crystals, but the inherent character of the crystal remains the same. What is that inherent character? That is the angle. Interfacial angle remains the same between the two atoms. This is what the third point says. In spite of the different sizes and shapes of the crystal of the same substance, it is observed that the angles between the corresponding faces, called the interfacial angles of the crystals of a particular substance, are always the same. This is called the law of constancy of interfacial angles. The instrument used for the measurement of interfacial angles is called a goniometer. Let us take an example. Interfacial angle in hexagonal structure is 120 degree and in cubic structure is 90 degree, irrespective of their size and the shape of the crystal. If a crystal crystallizes in cubic form, whether it is a big cube or a small cube, so we have the same angle, that is 90 degree. If take an example of sodium chloride. So when I take a graphite, the size of the graphite is small, or if the size of the graphite is big, the angle between the two carbon atom remains the same, that is 120 degree. This is what the law of the constancy of interfacial angles. Coming to the second one, the law of rationality of indices or intercepts. Now, here I have shown a diagram. Carefully you observe the diagram. The geometry of a crystal may be defined with the help of coordinate axes, all meeting at a point O. That means O is a point, and where all the three coordinate axes, that is x-axis, y-axis and z-axis, they meet at this point. That is called, it intercepts at point O. The number and inclination of these crystallographic axes are chosen in such a way that all the crystal faces either intercept them at definite distances from the origin or parallel to same of the axis, that is intercepting at infinity. So try to understand the meaning of this statement. It says the number and inclination of these crystallographic axes are chosen in such a way that all the crystal faces either intercept them at definite distances from the origin or they are parallel to some of the axes, that is intercepting at infinity. You take in the diagram the face ABCD. The face ABCD is parallel to y-axis. So when it is parallel to y-axis, this face, it will not meet the y-axis only. It cannot meet the y-axis. It cannot intersect the y-axis. Therefore, it is known as it intersects at infinity. Take the plane take the plane the ADEG. this ADEG is parallel to x-axis. Therefore, this will not meet, it will meet at infinity. This is what the meaning of the statement is. Now, the law says, the law of rationality of indices or intercepts, it says, the law of rationality of indices or intercepts states that it is possible to choose along the three coordinate axes unit distances, that is, let us be assume A, B, C as the unit distances, not necessarily of the same length, such that the ratio of intercepts of any plane in the crystal is given by LA is to MB is to NC, where L, M and N are simple integers like 1, 2, 3 or fractions of the whole numbers. I repeat the statement. The law of rationality of indices or intercepts states that it is possible to choose along the three coordinate axis unit distances, that is ABC, not necessarily of the same length, such that the ratio of intercepts of any plane in the crystal is given by LA is to MB is to NC, where L, M and N are simple integers like 1, 2, 3 or fractions of the whole numbers. The students, you are going to study this aspect in the next lecture once again. In the above diagram, A, B and C are the distances from the intercepts O on X, Y and Z axis respectively. Assume OL is equal to 2A. See the diagram. Okay, assume OL is equal to 2A. OM is equal to 2B. ON is equal to 3C. Okay, 2B means the length always on the x-axis is given as A, the y-axis on B, z-axis on C. Suppose if OL is equal to 2 centimeter, OM is equal to 2 centimeter, ON is equal to 3 centimeter, then these ratios, this is what it says. That is, the intercepts made by the plane LMNR 2A is to 2B is to 3C, where L is equal to 2, M is equal to 2 and N is equal to 3, which are the simple whole numbers. The numbers L, M and N thus used to represent a phase or phase, and this is also called wise indices. So wise indices are nothing but they are the integers of to know about the distances from the origin on x, y and z axis. This law is also called the Hoy's law of rationality of indices. This law was discovered by the Hoy, hence it is also known as the Hoy's law of the rationality of indices. Coming to the third one, that is the law of symmetry. The law of constancy of symmetry, it states that all crystals of a substance have the same elements of symmetry. That is the plane of symmetry, axis of symmetry and center of symmetry. Suppose if you take a cubic crystal, you take any cube, it is having totally 23 elements of symmetry. So like this, the different crystals have definite number of symmetry, hence the word, the law of constancy of symmetry. So this is the slide that gives the Steno's law of constancy of interfacial angles. The Steno was the scientist in 1669. He gave this law. It says the angle, the crystal has the same angle whether the crystal crystallizes in the small or the crystal is having a bigger size. So this is the law of rational indices. So the distance here, as I have said, OA, OB and OC. These distances are given as A, B and C. These A, B, C lengths remains constant whether we take these are in the simple ratios. Okay, so this once again you are going to study in Miller indices, which I'll be taking in the next class. So the third one, the law of constancy of symmetry. For cubic system we have totally the 6 planes of symmetry. We have totally 9 planes of symmetry. We have totally 13 axes of symmetry and 1 center of symmetry. In total we have 23 symmetry elements. You take any cube, this 23 remains constant. So in a cube we have 3 types. So one is the simple cube, another is body centered cube, third one is the face centered cube. In simple cube and face centered cube there is no center of symmetry, hence they have the 22 symmetry elements. In the body centered cube you have 23 symmetry elements. Thank you.